Now we are going to answer the question, what is a PLC? A PLC is a general purpose microprocessor based controller used in industrial applications. Using PLCs in industrial applications have several advantages. The first thing is that the hardware of PLCs has noise immunity measures which make the PLC the suitable controller for the industrial environments, which have all sources of noise and interference. So the hardware is, we can call it noise immune. It has modular structure allowing addition and replacement of units. We build the microprocessor system by adding modules to the system as they are required. You don't have to build full-scale PLC from the very beginning. You can start with simple modules and add modular structure to the PLC system as is required by the application. The main advantage of using PLCs is that they have standard input-output units with hardware interfaces for direct connection of input devices, which are normally the process transducers, and output devices, which are the process actuators. This connection does not require any additional hardware by the control engineer, as long as the output and input units were chosen correctly according to the requirements of the process. The final thing is that programming and reprogramming of the PLCs is very easy and they can be programmed on site. In this slide, we have a drawing representing the PLC system, which consists of a power supply and a CPU, which is the central processing unit of the PLC. It has memory space, which is divided into program memory and work or data memory. In addition to the input module and the output module, the input module to which the input devices are connected, the output module to which the output devices being controlled are connected, and finally we have the programming device, which is normally a PC with a special application on a DVD giving the programming environment of the PLC. The programming device is usually connected to the PLC during development of the program, testing and debugging. And after the program is completed, the programming device can be disconnected from the PLC. So the PLC does not require a programming device all the time during operation. The central processing unit is responsible for controlling and supervising all the operations of the PLC. The central processing unit is connected to the other parts of the PLC through a communication bus. The memory unit for storage of program, we call it program memory, and for storage of data and outcomes of internal functions during execution of program, we call it the work memory. The input and output units are the modules that give the required interface between the internal hardware of the PLC and the outside world coming from input device and output device. Input and output units operate at specific voltage levels, either AC or DC, and they are selected according to the intended input-output devices in the process, which are connected to the inputs are connected to the process transducer and outputs are connected to the process actuator. We should choose the input and output units with the operation voltage required either AC or DC by the input devices and the output device. Each input channel in the input unit has a specific status bit in the input memory with a unique address to store a 1 or 0 depending on the state of the input device connected to this input channel, whether it is on or off. Similarly, each output channel has a specific status bit with a unique address to store a 1 or 0 depending on the required control of the output device to be switched on or off in case this is in case of digital outputs and digital inputs. PLCs can deal with analog outputs and analog inputs, but it will not be considered in this course. We are limited to digital inputs and digital outputs. Finally, the programming unit is usually a usual PLC with the necessary programming environment running as an application program. Now we are going to illustrate how we select the modules of a PLC system. First, you have to select the main unit, which consists of the CPU and the memory space available in the PLC system, either for program or for work memory. By choosing the main unit, you limit the number of inputs and outputs that can be connected to the CPU by the maximum allowed input devices and output devices that can be interfaced to the CPU through the communication bus, and you limit the speed of the processor, and you limit the size of program that can run on this PLC. So it is very important to have thorough examination of the available main units of PLCs before choosing or selecting the main unit of the PLC system you are going to build. Afterwards, you choose the input and output units depending on the number of input devices to be connected to the PLC and the number of output devices to be controlled by the PLC. And you have to be aware of the voltage levels required by the process transducers and actuators. During operation, the PLC executes programs in real time from beginning to end, depending on the current values stored in the input status bits. During program executions, the program may change the values of the output status bits appearing in the program from 1 or 0. The input status bits contain 1s or 0s depending on the input devices connected to the PLC, whether they are on or off. And similarly, during program execution, you write 1s or 0s in the output status bits depending on the required switching of the output device to on or off states. So we have an input image containing the input status bits, and we have an output image containing the output status bits. Programs on PLCs are executed in continuous cycles, as will be shown in the next slide. In this slide, we have a diagram representing the 3 phases of execution of the program. We call it the PLC program scan cycle. The first stage in which the input image is updated depending on the states or the current states of the connected input devices by copying 1s or 0s to the input status bits corresponding to these input devices. Afterwards, the program is executed, and during program execution, output status bits are used to store the required 1s or 0s corresponding to the required states of the output devices, whether they are on or off. After program execution, we go to the last phase of the program cycle, in which output status bits are copied to the output devices. If an output status bit contains 1, this means that the output device should be switched on. If an output status bit has 0, this means that the output device is switched off. We have to know that program cycles are executed in a duration of milliseconds. So from the first phase to the last phase, the time duration of one program scan cycle will be in the order of hundreds of milliseconds. So that if any input device changes its state from on to off or off to on, it will not be observed until the input processing phase of the next program cycle. This provides or constitutes latency of reacting to the input changes. But usually an input device will maintain its value for longer than 100 milliseconds. So any change on an input device will not be missed. To give you an idea of the time of changing inputs in the real time, if we have push buttons, a push button pressed by a human being, this pressing will last between 200 and 300 milliseconds, and this is a very short time compared. So this is a long time compared to the very short time of the program scan cycle. So changes occurring on the input devices after the input processing phase is finished will not be reacted upon or felt until the input processing phase of the next program scan cycle. And as I said, the time for changing inputs is much longer than the program scan cycle, which is in the order of 50 to 100 milliseconds, and the change of inputs may last for 200 or 300 milliseconds. Programming instructions and addressing schemes used in PLCs depend on the manufacturer of the PLC, and they can change from one PLC manufacturer to another. In this course, we will adopt a Mitsubishi FX series PLC. Addressing of input status bits in the Mitsubishi FX series is based on a symbol X followed by an octal number, and addressing of output status bits is based on a symbol Y followed by an octal number. Logical functions described in PLC programs depend on simple logical operations which we call examine on and examine off. And in the shown truth tables, we have an input status bit x1, which may be 0 or 1, and the outcome of performing examine on this bit is shown in the truth table. Similarly, if we also use an examine off logical operation described by the shown truth table. We combine these logical operations with and, or, and not functions, so that any relationship between an output and input status bits can be described by a Boolean expression as shown in this slide. We have y1 depending on the ORing of two inputs, y2 depends on the ANDing of two inputs, and y3 is described by the shown Boolean expression.